Good morning, good afternoon, good evening, everyone. This is video 8 of Couplings and Monte Carlo, Stat 248. In this video, we'll start covering the material of chapter 4 of the lecture notes. And this is about using coupled chains in order to diagnose convergence, to remove burn-in biases, to obtain perfect samples. So really algorithms that employ couplings of Markov chains. So in this video, we'll start by looking at couplings of Markov chains that we can implement, and in particular couplings that result in the chains meeting, that is coinciding after a random number of steps. And then we'll start covering a method due to Wallin-Johnson to diagnose convergence that employs coupled chains. So we need to know how to generate coupled chains in order to apply the method. But we'll see that it provides a non-asymptotic convergence diagnostic. Let's start with a reminder of where we were last time. In the previous part of the course, chapter 3 of the lecture notes, we have looked at couplings of Markov chains to establish geometric ergodicity. Couplings were a proof technique to establish the geometric ergodicity property of various MCMC algorithms. So let's introduce again a Markov chain, XT. The Markov chain is assumed to be initialized at the distribution pi0. And for all times after 1, XT is generated conditional on XT minus 1 from the Markov kernel capital K. So different MCMC algorithms correspond to different Markov kernels. For such chain, we denote by pi index t, the marginal distribution of the chain at step t, at time t. And we have pi t converge to pi as t goes to infinity, pi being the target distribution that we would like to sample from. And so we can imagine the space of probability distributions. It's a complicated space, but we can imagine just a representation in the plane. And we would start the Markov chain from pi0, and it would go to another distribution pi as time progresses. And so pi t becomes closer to pi when t goes to infinity. So we can imagine a path from pi0 to pi, such as the one in this figure. And to formalize the convergence of pi t to pi, we have to specify a distance, for example, the total variation distance or the Wasserstein distance, or some divergences like Kullback-Leibler, etc. So the big technique that we've seen in this course to obtain such visual results with a geometric rate was the idea of coupling, where we introduce a second chain denoted by y, and this one is started from the target distribution pi. And it evolves like the X chain using the Markov kernel capital K. So yt given yt minus 1 is k yt minus 1 dot. But since it starts from the stationary distribution pi, yt follows pi at all times. That's simply from the pi invariance of the Markov kernel K, which is satisfied for most MCMC settings. So with this second chain, we can apply this reasoning of writing the total variation distance between pi t and pi as the total variation distance between the distribution of xt and the distribution of yt at time t. And using the coupling representation as an infimum, we find that this is less than the probability that xt is different than yt for any particular coupling xt-yt. And thus, by a careful design of the coupling between the two chains, we can obtain probabilities for such event xt different than yt that would go down to 0 geometrically fast. So they would be less than c times rho to the power t, where rho is between 0 and 1. But this whole construction above assumes that y is at stationarity, and thus that y0 is from pi, and in practice we do not know how to simulate from pi. That's why we're doing MCMC in the first place. So we cannot really simulate this coupling construction. It appears to be theoretical at this point. So without assuming that we can sample from pi, we will still be interested in coupled chains. And so we will start by looking at the problem of generating coupled chains on the computer, so implementing a coupling of Markov chains that will be denoted by xt and yt, like before, but those ones are initialized arbitrarily. And so we won't assume that any of those chains are started from pi. We will in fact often assume they are all started from pi 0, the initial distribution of the chain that might not be very close to pi. And among couplings of Markov chains, we will be particularly interested in generating Markov chains that meet exactly, that become exactly identical after a certain number of steps. So more formally, we're looking at chains such that there exists a meeting time tau, such that for all times after tau, xt is equal to yt. And we want the meeting time tau to be finite, almost surely, that is with probability 1. And in practice, we will also want the meeting time to have a finite expectation. So why would we like to be able to generate such coupled chains? So the point of chapter 4 is that there are methods, Monte Carlo methods, that rely on such couplings of Markov chains. So we can implement those methods if we can generate coupled chains that meet. And it's going to be the case that we would like the meetings to be as early as possible. So the random variable tau, we would like it to have the smallest expectation, for example. And those methods are going to rely on those coupled chains, and in particular on their meetings, on their meeting times, to estimate the total variation distance between pi t and pi for finite time t. For example, so again, the total variation, but it could be also other distances. Also, we will use such couplings to get rid of burn-in biases, that is, to get rid of the effect of the initialization on the estimate, on the expectation of the estimate. So the bias here refers to the difference between the expectation of a function under pi and the expectation of our Markov chain ergodic average. So this difference is not zero because we do not generate typically the Markov chain at stationarity. And so we will see that couplings allow the construction of unbiased estimators instead of those standard MCMC averages. And finally, we will see methods relying on couplings of Markov chains to obtain perfect samples from pi. So this is a remarkable class of methods called coupling from the past. But again, in order to implement coupling from the past, we need to be able to generate Markov chains that exactly meet. So for all of those reasons that we will explore in details in future videos, here we will first start by considering the problem of obtaining Markov chains, of generating Markov chains on the computer, such that the chains would exactly meet. Note that we will only look at a very small subset of all the possible techniques that we might employ for couplings. So let us first formalize the problem under consideration. We would like to generate Markov chains that meet. So we're going to denote them by xt and yt. They will be started arbitrarily, so from pi 0, both independently, for example. And they will both evolve marginally according to the Markov kernel k, corresponding to our MCMC algorithm. But we're looking for ways of generating those chains such that they will meet in a finite time, again denoted by tau and referred to as the meeting time. And so the trajectories of the chains might look like those x and y that meet exactly at a certain point here in the middle. And that instant will be called the meeting time. After the meeting time, you see the chains remain together. So xt is equal to yt for all times after the meeting time. And so we're looking really at the construction of such a coupling strategy. In other words, we're looking at implementable algorithms to generate xt and yt. And of course, that will depend on the choice of Markov kernel k, which is really the choice of the MCMC algorithm under consideration, whether it's Rosenbluth-Taylor, Hamiltonian, Gibbs sampling, etc. And note also that technically we will restrict our attention to constructions that are Markovian. This means that we will try to construct the next state xt plus 1 yt plus 1 given the current states xt yt, not using in any way the previous states or the states afterwards. So again, we can formalize this a little bit more. We are looking at Markov kernels k bar on the joint space of x and y. So this Markov kernel will go from a pair xt yt to another pair xt plus 1 yt plus 1 in such a way that if we only keep the x component, it's as if we have employed the Markov kernel k, the original kernel corresponding to our MCMC algorithm, and likewise for the y chain. But furthermore, there is a chance that the event xt plus 1 equal yt plus 1 might occur. So contrarily, for example, to an independent coupling on continuous state spaces, here we want to design a coupling such that this meeting might happen, which means that the probability of going from xt plus 1 yt plus 1 to the diagonal of the state space, xt plus 1 equal yt plus 1, should be more than 0, either for all xt yt, all starting points xt yt, or at least for some of them, and in that case for enough of them, so that it might really in practice occur. So next we will look at the case of Rosenbluth-Taylor-Hastings algorithm, and later we'll mention briefly some other MCMC algorithms. So let's look at the Rosenbluth-Taylor-Hastings algorithm. And I'll recall first how it works as a reminder, but this is material from chapter 1 of the course. The Markov kernel k here, in terms of the associated algorithm, or in pseudocode, what does it do? Well, given xt, first we propose x star from the distribution q xt dot. That's called the proposal distribution or the proposal kernel. And then we sample a uniform in the interval 0, 1, and we compare that uniform to the Rosenbluth-Taylor-Hastings acceptance ratio, which is the target evaluated at x star divided by the target at xt, multiplied by the ratio of the proposal densities in one direction and in the other direction. And if that uniform is less than this ratio, xt plus 1 is set to be x star. Otherwise, xt plus 1 is set to be xt. And so next we look at the problem of coupling this kernel to obtain another Markov kernel denoted by k bar on the joint space of two chains. And we would like to generate the next two states, xt plus 1, yt plus 1, given xt, yt. And we're going to look at a pseudocode to do that, such that there might be meetings. There might be meetings between the chains. So this is one particular coupling of this algorithm, perhaps the simplest one, but it's not the only one. There are references in the lecture notes. So here we sample x star, y star from a coupling q bar of the two proposal distributions, which are q xt dot and q yt dot. Then we sample again a uniform distribution, a uniform random variable in the interval 0, 1. And based on those two proposals and this unique uniform, we perform the acceptance rejection step for the X chain. So that's exactly as before. We compare U to the Rosenbluth-Taylor-Hastings ratio. And if U is less than this, it means that we define xt plus 1 as x star. Otherwise, we define xt plus 1 as xt. But now we also have to care about the second chain, the Y chain. And for the Y chain, we do exactly the same with the same uniform. So we accept or not yt plus 1 equal y star or yt plus 1 equal yt based on the comparison of the same uniform with this ratio where y's replace the former x's. And so in this construction, you can perhaps see that if we employ a coupling for q bar that would trigger meetings x star equal y star, then there's a chance that xt plus 1 might be equal to yt plus 1. And in particular, if q bar is a maximal coupling of the two proposals xt dot, qxt dot, and qyt dot, then there might be a chance that x star is equal to y star. And if the uniform is appropriate, we might then observe xt plus 1 equal yt plus 1 equal x star equal y star. And so the event xt plus 1 equal yt plus 1 might occur, and it occurs precisely when the proposals are the same and when they are both accepted. Note also that if xt is equal to yt in the beginning, then also we are guaranteed that xt plus 1 will be equal to yt plus 1. So the previous construction is an example where the event xt plus 1, yt plus 1, xt plus 1 equal yt plus 1 might occur. But is it likely to occur? And that's another problem, of course, that will depend on the particular choice of target distribution and proposal distribution. But there's a good reason to suspect that for the random walk Rosenbluth-Taylor-Hastings algorithm, this particular coupling from the previous slide, in high dimensions at least, might not lead to meetings very quickly. They might occur at some point, but it's unlikely that it will occur quickly. And to see why, assume simply that the two proposals are Gaussian distributions. So qx dot is a normal centered at x with variance, for example, sigma squared times the identity matrix, so the same proposal variance on all components. And likewise for the qyt dot. Then the probability that at the next step of this coupling we'll observe a meeting, given the current state xtyt, well, is less than the probability of proposing the same state. Here I'm assuming that xt is different than yt. So we have this inequality, because we need at least x star to be y star for the two chains to become identical. And this probability is, by definition, if we employ a maximal coupling, 1 minus the total variation distance between those two proposal distributions, which are two normal distributions. And in the case of normal distributions, we can somewhat manipulate the total variation distance to get that this is exactly the probability that a chi-square with 1 degree of freedom would be more than the square distance between x and y divided by 4 sigma square. Right, this is something that you can show. And furthermore, by Markov's inequality, this is less than 4 sigma square divided by the square Euclidean distance between xt and yt. And the calculations are detailed, for example, in an archive report by O'Leary 2021 called Couplings of Random Walk Metropolis Algorithms. And so what do we see here? That the probability of meeting is going to get small when the distance between the chains gets larger. So if xt minus yt bar, which is the Euclidean distance, is large, the probability of meeting might be low. And so that's an upper bound that is not very sharp, but that provides already an intuition about why the chains should be closed for us to expect a possible meeting. Note also that the variance sigma square in d-dimensional settings is typically chosen as a constant divided by the dimension. So if you're trying to target a d-dimensional posterior distribution, for example, you might want to set the variance of the proposal to be of the order of 1 over the dimension in order for the acceptance rate of the algorithm to remain stable, to not go to 0 or to go to 1. And so overall, it means that the meetings might occur, but it's much more likely if the chains are close here in Euclidean distance relative to sigma square to one another. So this suggests that using maximal couplings alone might not work really well, because unless by chance the two chains happen to be close by, the chance of meeting is typically low. But perhaps we can combine those maximal couplings with other types of couplings that would be contractive, such that the chains would be designed to get closer to one another as time progresses, and then meetings are more likely under the maximal couplings. And for contractions, we will look at common random numbers strategies. So we'll look at contraction couplings, and then we'll talk about how to combine different types of couplings. So first, we consider the problem of designing now a contractive coupling. That is not necessarily a coupling that triggers meetings. That might be done appropriately by the maximal couplings if the chains are close by. So now we're looking at the problem of getting the chains to be close by. And so there's no general rule on how to construct contractive couplings, but it's a surprising, perhaps empirical finding that common random numbers strategies, CRN, work well in many MCMC settings. So to be precise, we write xt plus 1 as a function psi of xt and ut plus 1, where ut plus 1 is a random number. And then we evolve the y chain using the same random numbers. So this is the iterated random function representation of the chains, where we employ the same ut plus 1. And so this implicitly defines a Markov kernel k bar on the space of both x and y, a Markovian coupling. And in itself, it's not expected to lead to meetings, although in discrete spaces, it would lead to meetings. And we've seen this already, in fact, in the case of the Gibbs sampler in the Ising model, which is a discrete example, where using common random numbers on a naive standard implementation of the Gibbs sampler will, in fact, lead the chains to meet exactly, and quite quickly, in fact. But in general, for example, on continuous state spaces, if we employ Rosenbluth-Taylor or gradient-based algorithms, we might expect this to lead to a contraction, this common random number strategy to lead to two chains that go closer to one another. We observe it in many empirical cases. although it's not necessarily easy to show mathematically. And so examples that have been treated quite thoroughly in the literature are Langevin-based Monte Carlo algorithms, like unadjusted Langevin algorithm, for example, or Hamiltonian Monte Carlo methods, and many variants of them. They've been shown, in fact, to lead to contractions when employed in common random numbers for multiple chains. Also, it seems to work, and it has sometimes been proven in certain Gibbs samplers or slice samplers, which is an example seen in a notebook on the Canvas website. Note also that in one dimension, common random numbers is often equivalent to optimal transport. Or more precisely, when we use common random numbers in inverse transform sampling, inverse CDF sampling, in one dimension, we often get exactly the optimal transport strategy that is designed to minimize the expected distance between the variables. But apart from this one-dimensional case, it's rare and it's case by case that we can establish the contraction properties of a coupling, and in particular a common random numbers coupling. But it's easy to implement and to observe whether the chains contract or not as time progresses. There is not much of a full theoretical understanding. It's at the moment much more understood on a case-by-case basis. And so next we're going to assume that we have a strategy for obtaining contractive chains. And we had the previous strategy to obtain exact meetings with the maximal coupling IDs. Next, we'll look at combining those strategies. That is, combining multiple Markov kernels to obtain chains that meet as quickly as possible. There are many ways of combining kernels. I'll mention two settings. The first is where we assume that we have two couplings of the same kernel. So we have k bar and k tilde, for example. K bar leads to contraction, and k tilde leads to the possibility of exact meetings, but realistically only when the chains are already closed. And so we would like, of course, to use the contractive coupling until the chains are close by, and then try to obtain an exact meeting using the k tilde kernel. And again, if there are both couplings of the same kernel k, then we can decide on whether to use k bar or k tilde based on the current state xtyt without changing the marginal distribution of the chain. So it's a valid strategy to obtain a third coupling that is contractive when the chains are far, and so we need to compute some distance. And when the chains are close by, we employ the kernel k tilde that might trigger exact meetings. If the chains are far away, then we employ a contractive coupling in the hope that in the next step, the chains will be closer to one another so that we have a chance of using the k tilde kernel. And so this is called in the literature, for example, on Langevin and Hamiltonian Monte Carlo, a two-scale coupling, because we use either one or another coupling depending on the distance between the current chains. Another scenario, slightly different, is when we have two different kernels. For example, we have a Hamiltonian Monte Carlo K and Rosenbluth-Taylor-Hastings J. And we have a coupling for each, so K bar, which is, for example, common random numbers of Hamiltonian Monte Carlo, and J tilde, which is, for example, maximal coupling of the proposals in Rosenbluth-Taylor-Hastings. Thus, the latter allows exact meetings. So if both of those kernels, even though they are different, are pi invariant for the same target pi, then we can employ a mixture of those two kernels to obtain yet another kernel that is also pi invariant. And that leads to this following strategy for coupling. We employ k bar with some probability, omega k, Otherwise, we employ J bar, probability omega j, such that omega k plus omega j is equal to 1. And so intuitively, we might want to choose to use the contractive coupling with large probability, and with small probability, we attempt a meeting. And that combined strategy might result to faster meeting than if we try meetings at every step. Next, we look at a variation of the previous constructions in the case where we want to couple more than 2 chains. So assume C is an integer larger than 2, representing a number of chains. In some methods, we need to propagate those C chains. And so if we employ common random numbers, it's pretty straightforward what this means. It means we use the same random numbers in all of the C chains, exactly like we did for 2 chains before. And so it's going to be written here for chain 1 with a superscript parenthesis 1, and then x2 evolves with the same random noise, denoted by ut plus 1 here, dot 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 all the way to the Cth chain number C, still employing the same random number. So there's no conceptual difficulty of imagining common random numbers when there's any number of chains. The difficulty is more about maximal couplings. Maximal coupling strategies for C chains raise more questions, meaning there's more than one way of doing it, basically. And so we'll take an example for concreteness. Again, Rosenbluth, Teller, Hastings, with a proposal distribution Q. When we had 2 chains, we considered the maximal coupling of Qxt dot and Qyt dot. And so here we could iteratively obtain a construction where we would consider the maximal coupling of the first 2 proposals, xt1 dot and xt2 dot. Having obtained this draw, we can then construct a maximal coupling of x2 dot and x3 dot, etc., until we have generated the capital C proposals. But here the order matters and seems quite arbitrary, right? So if the label of the chains maybe should not matter, and this construction of a coupling does depend on the order of the labels. And so, for example, what we might prefer to do is to select the order, for example, to maximize the number of observed meetings expected per step, and thus maybe based on the pairwise distances between the current C chains, we might want to try certain maximal couplings more than others. Right? So maybe one should be coupled with chain number 5 and the second one with chain number 7. So there seems to be open questions regarding how to perform such couplings. So now, going forward, we'll assume that we have a strategy to generate 2 chains that would exactly meet. Or 2 chains, or in fact, any number of chains. So from now on, we assume that we can generate Markov chains that each follow the same evolution described by the Markov kernel K, but jointly meet at a certain finite time. So what can we do with such chains? Such chains that evolve and then meet, become all identical. So that's really described in many places in chapter 4 of the lecture notes. And we will start with a convergence diagnostics, diagnostic of convergence of the chain, due to papers in the mid-90s, in particular Reuter and Johnson 95, Johnson 96, 98. So please have a look at the lecture notes for the exact references. And so in this method, we consider C chains, more than 2 C. C will be, for example, in the hundreds or thousands. each of those chains will be started from the initial distribution pi 0 and will evolve marginally using the Markov kernel K. So individually, it's one of our chain of interest. And we'll assume a meeting time for the entire set of C chains. So the meeting time denoted by tau C. After tau C, all the chains are identical to one another. So xit is equal to xjt at all times after the meeting time for all chain ij. So there will be a big assumption of this method. We'll go back to it later. It's a big limitation of this method. Is that there's a certain event that occurs, and the event is that among the C chains, there's one with label S. So S is an integer between 1 and capital C. There's one of those chains that is as if it was at stationarity. Even though we actually started all of the chains from pi 0, once we have all of them, we look at them and we say, well, it's possible that one of them would be at stationarity and we wouldn't see the difference. In other words, the event occurs with some non-negligible probability. And in fact, we're going to write this probability as 1 minus r to the power c. So c is the number of chains and r is between 0 and 1. And r represents a rejection probability. So we can think of this r value as the rejection rate of a rejection sampler that would employ pi 0 as a proposal and target pi. So again, r is the rejection probability from pi 0 to pi in a rejection sampling algorithm. And of course, that's an assumption, right? So if we have a given pi and a pi 0, it might not be obvious that there is such an R and how large or small it might be. And of course, it assumes also that rejection sampler works, so that, for example, we can find, in practice, if we wanted to do rejection sampling, we'd have to find a bound on the ratio pi over pi 0, the ratio of densities. And so this assumption is not innocent. It's quite a large assumption. But then, if we are okay with it, let's see what it provides. We look at the probability that the meeting time is larger than t, and we decompose this probability into the two events. The event that described above occurs and the complementary. So that's the law of total probability. And then we just drop the complementary term, which is non-negative. So we can lower bound it by 0. And then we have that the probability that the meeting time is larger than t is like the probability that any of the chain will be different than the stationary one at time t, multiplied by the probability of the event. And by the coupling representation of TV, we obtain a TV on the right-hand side between pi t and pi. And it's quite remarkable because this works for all times t. And it yields a bound, an upper bound, on pi t minus pi in TV. And the bound depends on the number of chains C, the constant R, and the survival probabilities of the meeting time. So to be precise, we obtain the upper bound by putting 1 minus R to the C on the left-hand side, dividing by this. So let's summarize what can be called Johnson's diagnostic of convergence for MCMC. We assume that we can generate C chains, and so many times in parallel, in many independent instances, we will generate C chains until they meet, until they all coincide, and we will record the meeting time. So we will obtain independent copies of this random variable tau c. And from those observed realizations of the meeting times, we will be able to estimate an upper bound on the TV from pi t to pi by estimating the survival probabilities of the meeting time first. So we plug in any time t that we might want, even time 1, time 2. There's no asymptotic argument here, so we can plug in any t. And this probability, which we don't know analytically, we don't know exactly what it is, but we can approximate it using our realized meeting times, using our observations, so to speak. And basically, this is a Monte Carlo calculation, simply replacing a probability by an average of indicators. So here, tau Cn represents the nth independent copy of the meeting time tau c. Okay, so we have a way of approximating those survival probabilities using independent replications of C chains coupled to meet. And so then we can compute this estimated probability multiplied by the inverse of 1 minus r to the c, of course, provided that we have a value of r to plug in. Again, what is r? It's the rejection probability of a rejection sampler from pi 0 to pi. And so if r is even close to 1 when c is large, r to the c might be close to 0. And thus this whole multiplier might be not too far from 1. But if that's not the case, then this multiplier is huge and the upper bound is not useful. And so then ensues a question that is fairly difficult of plugging a value of r. And that's a matter of how much you trust your initial distribution pi 0 to be close to pi. So if you trust that, for example, 1 out of 100 chains started from pi 0 would be equivalent to being started from pi, then you would put r to be 0.99. Again, that would mean starting from pi 0 is like starting from pi 1 time out of 100. And that's usually quite a subjective assessment, of course, because actually computing this probability would be typically time-consuming. So this is something that the user plugs based on their general impression. But even if r is 0.99, so pretty close to 1, note that if c is 100, r to the c is much less close to 1. It's not actually that close to 0, it's around 0.37. And if c is equal to 1,000, then 0.99 to the 1,000 is very close to 0. And thus the upper bound on the total variation distance of interest might be hopefully not too large. Again, to summarize the limitation, this method assumes some proximity between pi 0 and pi, which is not ideal in large dimensional settings in particular. But the strength of the method is that it provides a truly non-asymptotic assessment of the convergence, because there is no assumption that little t must be large or large enough. It's truly non-asymptotic. I refer to the articles of Wallen-Johnson for concrete examples on how to use the method and how to interpret the results. We're reaching the end of this video. So we looked at how to generate coupled chains so that they would contract and eventually meet. One example of the use of such coupled chains in Monte Carlo algorithm is in the diagnostic of Wallen-Johnson that employs C chains generated then many times to obtain meeting times, and then those estimated realized meeting times are used to obtain an upper bound on the total variation distance between the chain at step t and the limiting distribution, the target distribution pi. There were limitations. We've seen that this method assumes some notion of proximity between the initial distribution pi 0 and the target distribution pi. So in the later video, we'll look at another type of method based these times on only 2 chains, but then again generated many times, but 2 by 2, that will provide upper bounds on total variation distances without assuming necessarily that the initial distribution is close to the target in any sense. And we'll see that next time. Have a nice week.